Okay, so we start. So today we want to do the lab session for bugging random forests and boosting. Then that we do exercises. So exercises, exercise 10. It's available on Blackboard. Some questions are not, 100%, clear. Are kind of open questions. But basically, we want to compare the bugging, boosting random forests and the maybe possibly some other methods such as KNN and logistic regression. And that should be useful for many of your final projects. And final project plan, I have already graded the, I have already commented your projects if your presentation is on the first day. And I will do tonight for the presentations on April the 21st. So I think I have already commented the several ones, maybe on the Polar, maybe, and the Priyankar and the Connor and so on. And today I will, oh, thank you. Today I will comment on the Brennan's one and maybe other things, maybe Marim and so on. Yeah. And you can include the more models as you study, the regression tree, support vector machine, and so on. So you don't really have to exactly stick with your original plan. You can extend or you can modify it if you have trouble to analyze data. And I updated some slides. Actually, the chapter 8 lab session. I just added some explanation on it and maybe some a few additional lines. Yeah. So last time that we did regression trees, and the regression trees usually don't have enough power to compete with other statistical models. So we have to use basically bugging random forests. So the last time that we studied how to fit regression tree, and that may be important for some to understand the basics, but in reality, that you have to use the random forests for bugging, boosting in most cases. Okay, so here is the way to fit the bugging and random forests. So remember that only the difference between bugging and random forests are the number of variables for each tree. So suppose we have only the two predictors and x1 and x2. But we don't really have to use all variables every time. So maybe the first tree is only based on x1 and the second tree is only based on x2. Still, if we take average of these two trees, then we have more complicated prediction surface. In this case, okay, so the first, okay, so suppose this is the first tree and this is second tree. And first tree, I put the information of the first tree in the dotted line. Then you can see that this area is, predicted as true for both trees. So we have higher probability, higher fitted probability. And this part and this part, they're predicted as the true for one of these classes, and the remaining part is not predicted as true for both trees. So even if we use only one predictor at that time, still the average of several trees makes the more complicated surface. So, and bugging, that we always use all variables, all predictors. each time. And random forests are few predictors at that time. And it sounds the bugging is more comprehensive, but actually the random forests usually the performs better. So it's a kind of mystery, but the random forests, since we have different kind of trees each time. So actually we diversify trees. So the result is actually often better. And these two procedures are fit by the same function, which is random forest function in the random forest library. So we use the car seats data in ISLR package. So we need these two packages. And the code for the bugging is the random forests, the response variable tilde, and the predictor variables, and then data set, and the we use the subset of the data set also. That is one option, and the number of trees. So this is the number of predictors to use each time. And actually the car seats data that we have the 10 predictors, so P is equal to 10. So if M try is equal to 10, that we fit the bugging. And if M try is smaller, that is called random forest. Yeah. Importance through this is just an option to see some outputs. So once you fit the random forest, you can see the importance of each variable. So we are predicting the sales of these car seats by other factors such as the comps price or income level or, in the area the store is located, or the advertisement amount in the market, or the population price of the car seat, and the shelf location, and so on. And you can see that okay, so we have two columns, and both of these indicates the importance of the predictors. So percent increase in MSE means that if we dropped specific variable, how much the mean squared error increase. So for example, if we drop the comp price, then the MSE will increase by the 17.7%. So somewhat this variable is important. Maybe more important variable is price or shelf location, because we have larger increase in MSE. And this is based on the out-of-buck estimation. So we evaluate the percent of increase in MSE in terms of out-of-buck estimation. So it's a kind of similar to cross-validated error, but actually the more incomplete version of the cross-validated error, but more quick to calculate. And the second column is similar information. So the increase in node purity. So so if the variable is dropped, how much the node purity, actually the decrease, or the inclusion of this variable, how much the inclusion of this variable increase the node purity. And the node purity is basically the RSS, residual sum of square for regression, and the so-called the Gini index for classification. Yeah, so maybe I do that. So so yeah, node purity is decreased. So the increase in node purity is the decrease in node purity average over trees when the variable is dropped. Well, we can say that the node purity is, this is the increase in node purity if the variable is included. And for regression, there's so the residual sum of square is used, and the classification, the Gini index is used. So Gini index is often used as inequality of some variable, but the exact definition here is this: basically the summation of all possible difference between the elements. So when the x sub I is the fitted probability of success for each observation, this is the summation of the absolute value of xi minus xj. Yeah. So anyway, so this first column and the second column indicates the importance of the variable. I think that probably the biggest difference is the first column is out of back estimation, and the second column is the usual in sample training type error. And we don't have any statistical interpretation, so we don't see which the variables are significant. This is just the descriptive statistics in statistical sense. So we say that the, for example, the price or shelf location, that is, reasonably, important. I mean, somewhat important, because if it's dropped, then the MSE increased by a large amount. So we have that descriptive statistics, but we don't have any statistical significance or testing. So yeah, so these are slightly different, relationship. Yeah, so for example, yeah, so this number is slightly larger than this, but this number is slightly smaller than this. So these two are slightly different measures, but both represents the importance of predictors. And this is a graph for that. So shelf location and the price are more important than other variables. And maybe comp price, advertising, and age, these are second more important variables. And the others have probably impact on the MSE, but the contribution is smaller. We can use the predict function to get the predicted value. And this is actually the 0, 1 yes or no prediction. So the random forest is sorry. This is continuous predictions. This is regression. So we just calculate the fitted value. And for classification problems, this returns the 0, 1. So that whether a specific observation is predicted as true or predicted as false. And to get probability, that we need the type is equal to probability. For classification. So remember that the tree-based method is for binary classification. And usually the predicted value is the binary 0, 1, but also that we specify type is equal to probability option to get fitted probability. So the tree-based method, so the usual regression classification tree, that we just split the data set into several pieces, and this is yes, and this is no, and this is yes, and this is yes, and this is no, or something. So the predicted value is only 0, 1. But the random forest, we take average of many trees. So we can calculate the predicted probability. So for example, if we have 5 trees, then we take average. So if 4 of the 5 trees predict certain observation as positive, then we can say 4/5, so 80% is the fitted probability. So random forest boosting, we can calculate the fitted probability for classification. For this example, that this is sales is continuous scale, so just the predicted value, so fitted value. Yeah, do you have any questions so far? Okay, so, and the next one, okay, so I plot the actual sales and the predicted sales for training data. And we make, I made a scatter plot for this. So this is predicted and this is actual. And you can see the correlation is pretty high. So it's predicted pretty well. So actual is about 10, then the predicted value is also about 10. And this is the training error, 0.477. How about the test data set? We can use the predict function for test data. So we specify the new data is equal to the test data. Then we can plot. And you can see still the correlation is highly positive, but the relationship between predicted value and actual value is weaker. So you can see this is very high correlation, maybe 0.98 or something, but here probably correlation is lower, maybe 0.8 or something like that. Almost always the test error is larger than training error. And actually, if we calculate the MSE, mean square error for test data, that is 2.87. So this is the 0.477, but this is the 2.87. So this is pretty large. We haven't done any cross validation or something, so just we fit the random forest without anything. So we make basically a very large tree. I forgot the default value, but basically this random forest function makes a large tree, and we just use it as the predicted value. So it overfits the data. So training error is small, but the test error is large. Yeah, so we optimize some parameters by cross validation, then probably that we can get more reasonable results. Yeah, for this specific example that I don't cover cross validation, and I don't really know if we have the ready-made cross validation function, but always you can do resampling. The cross validation, you can apply cross validation for random forests, so you can optimize some parameters such as the number of trees and the number of nodes. Yeah. And the next one is random forests. So this is basically the same, but only the difference is the number of predictors allowed for each tree is smaller. So here the p is equal to 10. So often we use p over 3 or square root of p. In this case, both are about 3. So I used M3, MTROI is equal to 3. And we do the same thing, and we calculate the predicted values, and we check the relationship between the actual sales and predicted sales, and we see the very high correlation. And here the MSE for training set is 0.649. So previously this was 0.477. So it gets larger, so it gets worse. But when we do the prediction for test set, that is more fair way to compare it. Actually, this MSE is 2.95. So 2.95 is which? Yeah, actually, in this case, random forest, the performs slightly worse. 2.877 and 2.9. 952. So it still performs slightly worse. Yeah, so yeah, so I think we have to optimize several parameters to get better results for random forest. Yeah, from the textbook, it's not entirely clear what is the best way to optimize the random forest. We can change the number of trees. That may be the one indicator, one hyperparameter. Number of trees. Yeah, but yeah, so it doesn't really discuss the many things to maximize. The random forest function also can change the node size or the maximum number of nodes and so on. So if you fine tune these variables, then probably random forests performs slightly better than this. Yeah, you can search the help of random forest function and see what kind of parameters we can optimize. Yeah, any questions so far? Yeah, so the next one is the boosting. So boosting is gradually determining trees or determining regression results. So each time that we reflect only a part of the regression results, maybe just 1% of regression result. And after that we regress response by predictor and we reflect just 1% of fitted value, then we use the residual to fit the model again. Then we slowly adjust to the we slowly determining the fitted value of the model. So that is the boosting. So to be exact, we fit. Okay, so at first we define the residual is equal to y, and we fit y over x, then we get the residual. So maybe I would say this is the R0. Then we get the residual R1, maybe R1. Then we have regression results. So y is equal y, regress y on x. So we have the y is equal to the ax plus b plus r or something. So that we reflect just the 0.01 times this fitted value. Then we define, maybe the residual, we shouldn't do that. Maybe we define the R1 as the y minus the 0.01 times fitted value. And then the next step that we regress the R1 on x and we repeat. And we repeat many times, then that we get the fitted value finally. So random forest, always that we fit y on x, but the boosting that we calculate residual, then we fit residual on the predictors. So slightly different method, more sequential method. Random forest is just a kind of average of several experiments. And we use the library, the GBM. The GBM stands for what? The generalized boosting methods package, so GBM. And we use the mass library for Boston dataset here. And the Boston dataset is here. So 506 observations of 14 variables. And often the median house value of the data is the response variable, and the others are predictor variable. And the others are predictors. Yeah, and we set the training set and the test set, and we use the GBM function to fit the median house value on the other variables. And the data set is the Boston training part. So I randomized, and I used half of the data set as training and the other half as test. And the distribution is, we have several options. The Gaussian and probably the Bernoulli are the options. Gaussian is usual for the continuous response, and we use the squared error as a criterion. Bernoulli is the case for the classification. And this is the number of trees, so 5,000. Yeah. So we basically repeat procedure for 5,000 times. And the interaction depth, so this is the number of variables used for each tree. So I used D. So remember that in boosting also that we use only a few variables for each regression. So actually this data have the 13 predictors, but each time we only use up to 4 predictors. Yeah. And this is the summary of the boosting results. And this looks a little poor, but you can see that the relative importance of each predictors. And actually the labels are not fully described here, but actually the first one is the L-stat. L-stat is what? Yeah, so you can see the R help to see what that means. L-stat is actually lower status of the population. So the percentage of lower status of the population. So that determines house price. That is almost obvious. And the next one is RM. RM is the average number of rooms per dwelling. So of course, larger houses, then higher price. So it's reasonable and so on. So these two variables seems the most important. And other variables are still somewhat important. That this is the DIS is the distance to Boston employment centers, and the CRIM is the crime rate. Yeah, and so on. But other variables may be somewhat important. And we can also see some kind of fitted plot or something, so that we see the predicted value by each of the predictors, predicted value, the fitted value for response Y by each predictor, predictor. the number of rooms and the price. You can see the number of rooms increases, then the price increases. So if we use only one tree to regress the y on other predictors, maybe the result looks like this, right? But since we have taken several averages, so that we have this zigzag pattern. So it's more kind of detailed curve between the predictor and the fitted value. You can see that this is a kind of zigzag pattern, especially you can see here or here. And I believe that this is because just we see the fitted value by one predictor, but actually the tree is based on more predictors. So other predictors are used to calculate fitted value. So even if all division, so all threshold means the higher number of rooms means higher price, still the other variable comes in. So possibly some observations are larger, some fitted values are larger, even if the number of rooms is smaller. For example, so these ones, yeah, so the number of rooms is the average number of rooms in the town, so it's the fractional. But maybe, okay, so suppose that these observations may come from some cities where the distance is closer to the employment center. Then this observation comes from a town which has a larger number of average number of rooms, but maybe more distant from the city center than employment center, then possibly the house value is lower. So that's why this is not entirely monotone. So the other one is this one. So again, LSTAT is lower status of population. So the percentage of lower status population is smaller than the house value is higher. So we have the negative relationship between the two. And certainly the relationship is not just linear. So here almost flat, but here we have a steeper curve. So random forests can reproduce these kind of curves. Yeah, and the fitted value, and if we calculate the root mean square error for test data set, this becomes 3.776. So this is the root mean square error for the fitted value y. So y typical value is probably 15 to 30, and on average we have the error size of 3.77. Actually, when I designed this course, before I started to run this course, I had more smaller. I have a smaller, the directed study to study this book with a couple of students. And at that time, I used all kind of methods to predict this Boston data set, and we calculated cross-validated errors. And the benchmark is like 4.5 if we use just linear regression and stepwise selection. Then we get the RMSE of 4.5 about. And if we use all interaction terms or using support vector machine or something like that, then about 3.0 is the possible cross-validated RMSE. So the 3.77 is certainly better than just a linear model, but actually it does not perform as good as some models, such as the regression with the three-way interactions. Yeah, so this is the today's one, and now I want to do exercises. Do you have any questions so far? Okay, so I opened the exercise 10. I think that should be available in Canvas, so you can download it. And yeah, so this is the exercise. So we are using a Caravan dataset, and this is actually the modified exercise from the textbook. The Caravan dataset contains the 5,822 the real customer records on whether or not they purchase some certain product. I'm not exactly sure. Product ownership of some insurance, yeah, insurance policy. So we have basically 85 predictors, mostly categorical predictors, and one response variable, which is whether or not the customer purchased Caravan insurance policy. Caravan, maybe a company's name or the type of insurance, I don't know. Yeah. So our goal is to identify which customer will buy the insurance product. For example, that we are sending the direct mails to promote a product, but we want to send to the potential customers who have higher chance to buy the product. So that is typical business question. Yeah, so this data set is included in ISLR library, so you can read the data. Then at first, we split the data set into training and test. Then we do boosting to get the prediction. Then we make prediction. And actually in this data, the most customers did not buy the insurance policy. So actually the predicted probabilities are all small. So we just want to identify the group which has more likely to buy than other customers, even though, you know, the chance is not more than 50%. So we set the threshold at 20%. Then we see if this prediction makes sense or not. And we compare, hopefully we compare the result with the random forest, KNN, and logistic regression. So that is the question. Okay, so now we want to split the group, the breakout session. We have the 7 students here, so we split this into 2. So breakout rooms, maybe 10 to 15 minutes. 1, 2, 3, 4, and 1, 2, 3. Yeah. Okay. So, okay. Enjoy conversation for 10 to 15 minutes. it sounds the discussion wasn't really active, so I just terminated in 10 minutes. Do you have any questions on how to do the questions? No.
After B, what kind of a distribution was Gaussian okay to use?
That's a good question. So this is a classification question. So the Bernoulli is the distribution to be used. So
I'd get an error.
Yeah, probably that's right. Oh yeah, right. Actually, this function so this function needs the 0, 1 numeric value 0, 1 for classification problem. So this may be a little special for this function. So okay. 0, 1, then we have to specify the Bernoulli function, Bernoulli option as distribution. So this is classification. So Gaussian is used for continuous variable. Okay, maybe I will do this. Okay, so at first we have to set the test set and the training set. Then after that, we do boosting and random forests. So yeah, so we need the ISLR package to use the data, Caravan data. So library, the ISLR for Caravan. And we need the library and the GBM for boosting for GBM function. And later we use other methods, maybe just in case we read tree library. I think that this maybe some function we need this. And at first we do the training and test. So yeah, so actually for this specific function, the GBM function, okay, so maybe I see at first the maybe structure of the Caravan. And you can see that we have the 86 variables, and the most variables are categorical variables, and we have many variables, and the last one, the purchase or not. So this is the response variable. And I believe that this is 1 if not purchased, and 2 if it's purchased, or just the no and the yes. So factor variables are interpreted as 1 and 2 if we make it numeric. And we actually have to make this into 0, 1 or 1, 0. So we at first transform this variable into purchase. Transform it into numeric variable with 0, 1. So at first, okay, so this variable is factor variable. So the factor variable to numeric variable, then no becomes 0 and the yes becomes 1. But we want to make it the 0, 1 variable. So no yes to 0, 1. So we subtract 1, then no becomes 0 and the yes becomes 1. caravan. So caravan. Okay, caravan. Okay.
You need to change the first one.
Oh, yeah. Caravan. Both I mistyped. Yeah, caravan. Yep. So then the purchase variable becomes 0, 1. We can see that the caravan purchase, maybe we can just ahead first 10 observations, then 0, 0, 0. Maybe if we make it larger, some ones. So, but only a few customers purchased this product. Then we set the training set and the test set. So we set the training set as the first 1,000 observations. So it seems this is already randomized. So the textbook mentioned that just we can make first 1,000 observations as training. So usually the randomization is recommended. Yeah, okay, so it sounds, I always mistype caravan. Okay, so TRN is this. And the test set, TST is the 1,000 first observation to the last. And actually the size is the 5,822. So this is the test set. So this is for A. And now that we wanna fit the B, the boosting. So boosting, so GBM, so maybe we name it as GBM1, and this is GBM of the purchase on as a variable, and the data is training, and the distribution, Bernoulli, and the Bernoulli is probably the default class, so probably it's fine, but the just to make sure the distribution is Bernoulli. So last time that we did use the Gaussian because that was a regression problem. So this is classification. So Bernoulli is the standard one. And number of trees, 1,000. So we gradually grow the tree by, the 1,000th of the tree each time. And we don't have the hyperparameter lambda. Probably lambda is set as 0.001, and because the number of trees is 1,000. I don't know. Probably we can change the. Oh, actually no. Yeah, I'm not sure. But here that we want to make the shrinkage value is equal to 0.01. So lambda we set as 0.01. So yeah, I think that probably at least this is the number of trees is more than 1 over shrinkage, right? So the shrinkage means the we only reflect the 0.01, so the 1% of the original regression results. So even we repeat 100 times, still that we regress the 1% of residual each time. So we cannot get it at 100%. So probably the number of trees should be 100 or larger. So here the number of trees 1,000 and shrinkage 0.01. This is the numbers this textbook suggests. Maybe that we have a better numbers. And this is the thing we can do. Unused argument. Bernoulli.
It's distribution.
Oh, sorry, the T is missing. Distribution. Sorry, distribution. Yeah, so that's it. And some errors, the warning messages, we take only 1,000 observations and some variables are sparse. So all elements are 0 for first 1,000 observations. So probably this warning message is due to that fact. So variable 50 and variable 71 has no variation. So that often happens in real data analysis. Suppose that we are regressing the house value on several features of the house, and suppose that one column represents the existence of indoor swimming pool, then only 2 houses have that feature out of 1,000 observations. And if we make training and test set, and the training set, the no house has the indoor pool, then we cannot really examine how useful that variable is. And probably the same thing happens here. Yeah, but this is just warning message, and just unfortunately, we cannot evaluate those 2 variables, but still we don't have any error. And then summary, GBM1. Yeah, so this is the summary result. The most useful the variable has this contribution. I think that this is the percentage of percentage increase in MSE, and then this one is maybe 15% and so on. And we can see actually the variables here. So the relative influence of each variable. So I don't know exactly sure about the meaning of this, but the PPER, the SAUT, so this variable is most useful to explain the variation in whether or not the consumer buys that product, and so on. So probably we have to consider first maybe 20 or 30 variables, but after that the almost useless variables. Yeah, so now that we want to do the prediction and we want to summarize the data. So number C is the prediction by boosting. So first, we want to calculate predicted value. So I name it as the predicted value PRED of the training set. Just for demonstration purpose, we see the training error and the test error. So we target test error, but we calculate both. So predict GBM1 and the type response, then we can calculate the predicted value. So using 1,000 trees, so we can see that each tree just returns the 0 or 1 for each observation. But if we averaged over 10,000, oh, so sorry, the predicted the GBM. Yeah, I think the algorithm itself is not entirely clear, but using 1,000 trees, then we calculate the predicted values. So if we see the result, that these are just the probabilities for each observation. So first observation has the 10% chance to purchase the product, insurance product. And the second person, only 2%, third person, 6%, and so on. Yeah. Sorry, I'm not entirely clear about the exact algorithm, because every time that we fit the I'm not entirely sure about the algorithm of classification and the boosting. We fit the data. Probably we transform the response variable into continuous scale in some sense. Then we fit the model again and again. And this is the calculated probabilities for each observation. And now that we calculate whether each observation has more than 20% probability to purchase the product. In the first 10 observations, actually, none of them have more than 20% chance. So first 10 observations, none of them, but 20, no. But if we see the 50 observations, maybe this person is more likely to buy than other person, even though this is 37, 40, 42. So only 23% probability to buy the product, but at least more likely than other customers. Then we do make a table. So this is the actual purchase history, and this is the predicted purchase. So whether or not they have the more than 20% chance to buy the product. Then this is the result. So this is actually the people who didn't buy the product, and this is the people who actually did buy the product, and this is the false and the true. And actually, if predicted false, the only 43 people out of 972 people bought the product. But this group, if predicted true, then actually the 16 out of the 28 people that bought the product. Actually, it's more than 20%, but that's the result. And this is with the training set. So that we do the test set, so that we do the same thing for the test set. So at first, the predicted probability for test set, we can use the predict function in the same way, and we put the new data set as test data set. Then we do the dichotomization. So more than 20% probability, then we regard that person has a higher chance to buy the product. Then we make a table regarding this predictor. Sorry, yeah. Sorry, T. So this is the table. So you can see that the test set has the 4,822 observations. And if predicted false, actually out of the 4,677 observations, only 255 that bought the product. So only like 6%. But if the predicted true, so this smaller group with 145 observations, the 34 out of 145 bought the product. So 34 over 145. So that is the 23%. So about 20%, right? So bought the product. So you can see that the accuracy is not high. 4422 plus 34 over the sum of these all numbers. So TA, TST, this should be 4822. So this is accuracy. So accuracy of 92.4% does not make sense because anyway, so the majority of people don't buy the product. So if we think about the percentage of the people who buy the product, percentage of buying the product. That is 94%. So accuracy is even lower than that. So if in terms of accuracy, so predicting everyone don't buy the product, that is the baseline because most people don't buy. And actually the 92.4% is even worse than this 94%. So accuracy does not make sense, but certainly this prediction makes sense because if we wanna narrow down a specific group of customers who are likely to buy the insurance, actually it works. So if we, for example, send the 145 people a direct mail, then 34 of them they buy the product. So that is 23% and much higher than overall average of 6%. So it makes certainly sense. So accuracy, error rate, that isn't really a uniform, uniformly the best measure to evaluate the model. So this case, certainly this prediction makes sense. Yeah, so that's why we have several measures. For example, the specificity and the sensitivity. For example, out of the these 289 observations, actually the 34 actually bought the product. So this test has the sensitivity of the 34 out of 289. So that is maybe 12%. And so on. So we have several measures. So basically, we have several ways to set threshold. Often the prediction is done by using the 0.5 as a threshold, because more than 50% means they're more likely to be 1. But not necessarily 50% is the most meaningful threshold for real problems. So if we set different threshold for specific purpose, that can be useful. Yeah, random forests. We can do the similar thing, and actually we can get the similar results. Actually, here the boosting is better result, but I will upload the solutions for random forests to the Canvas. Do you have any questions so far? Yeah, and the E and the F, the KNN and logistic regression, we covered in chapter 4. So you can refer the chapter 4 lab slides to see how to do it. And certainly it's interesting to compare the results with these methods. Yeah, generally the tree-based methods are good for classification, but often we overfit the model. Okay, so if you don't have questions, that's it for today. So see you next Thursday, and